is, how do you take a problem that you're asked to solve, and how do you convert it into a formalization in terms of state space search? How do you go about doing that? And there's various ways to take a problem and develop a state space search approach to it. AI, again, is concerned with exploring alternatives, searching through alternatives. There may be no one algorithm that you could easily develop that would find an optimal course schedule for somebody, where optimal was defined in terms of what that student's interests were, trying to minimize the number of credits, but still exceeding the credits that were required for a major. And so what an AI approach does is it searches through a bunch of different schedules and evaluates each schedule that a student might prefer. And it's going to evaluate those in terms of a number of factors, but there's this notion of exploration or search. You come up with maybe many schedules and you evaluate them, and then you pick the best, or you pick some subset of the ones that you've developed as the best possibilities. This will often, we're going to talk about state space search first, but at least part of the reading and part of the lecture today is going to talk about state space search as searching an explicit graph. So we have a graph, the graph contains nodes, and we want to search that graph for some selected nodes called the goal nodes, and we'll talk about that. But typically, AI approaches are not going to be searching explicit pre-enumerated graphs. The AI algorithm itself is going to enumerate the various states or nodes of the graph as it goes. We'll come back to this when we've gone through a couple more chapters, but state space searches, there's a lot of factors here, whether it's a deterministic process or whether it has some probabilistic aspects, for example. We'll come back there. But in the most abstract sense, we're going to be talking about searching a graph with nodes, arcs between nodes. Neighbors are nodes that are linked by arcs. A path is a sequence of nodes in which adjacent nodes in the path are linked by an arc. And so you can follow some arcs from a start node to a terminal node in the path. The length of the path is simply the number of arcs. And when we abstract these problems, we're going to be starting from certain nodes and trying to find paths that take us to goal nodes. That's in the most abstract sense what it is that we're wanting to do. Here is an example of a delivery robot that the book has talked about. The robot is down here and the robot wants to be up here. So this is the goal location for the robot. This is the start location for the robot. And the book has a number of constraints, some of which are intuitive, some of which are not. But if we go here, I'm going to simplify just for the sake of this presentation. There are several ways that the robot can go from here to here. They could move through this room. They could move around the hallway and into this room. The book has some constraints that doors only open in the direction that are indicated here, and once you go into a room, the robot may not be able to get out all by itself. I'm disposing with those constraints. And this is how I would represent this in the simplest form or as a graph search. This is, you can think of as a graph in which this is one state in the graph or one node in the graph. It has an arc to adjacent locations. There's an arc from 0, 1, 3 to 0, 1, 0, 1, 0, 0, 1, 0, 1. So there's an arc here, there's an arc here, there's an arc here, and there's an arc there. And those arcs are represented up here. So if I started 0103, one neighbor is 0101, room 103, 0105, and then B3. Those are the adjacent locations. And so in our state space search, we would take the start state, we would expand it, we would get neighboring states. And then for each of those, depending on what the search strategy is that you've read about, we would select one of these and we would expand it. So 0101 would expand into TS, that's one of its neighbors, R10, 0103 is another neighbor. And notice that 0103 was the parent of this node, and 0103 is a potential child of this node. And then A3. So we're going to select these in some order, and we're going to expand them based on what the search strategy is. And again, I make some assumptions here that the book doesn't make. I simplify the problem somewhat because I just want to lay out what the general formalization is as a state space search. We're going to talk a bit later today, but primarily on Thursday, about what to do with repeated states, repeated nodes in search. We can't ignore it. We can ignore the possibility of repeats. That 0103 is repeated is something that the search algorithm, if we don't imagine that there are going to be many repeated states, we simply don't worry about it. We simply live with the repetition and continue search. You'll notice that I've outlined two possible paths here from the start state to the goal state. One, this one, goes along the hallway and into the room. The other, the shorter one, moves through room B and room C, taking a shortcut to R123. Notice that once we have a potential for a repeated state, this repetition, this pattern can appear repeatedly. And so if we're not careful, if we don't search for repeats and we choose a poor search strategy like depth first search might not be a good choice here if we had repeated states, then we can pursue a path that is infinite in length. And so your algorithm would not terminate. Questions about that? Again, if you read carefully the book, you'll see that you'll see what the alternative design here is, given some constraints there. Here's another simple problem that we can view as state space search. In some ways, it's more interesting. This is sort of like a Pac-Man-like game. Rob is some player, maybe an AI player. And Rob is supposed to collect a number of coins without running out of fuel and end up in location 1-1. Location 1-1 is not shown here in this illustration. This is a small part of the game space. Rob is currently in location 5-8. There's fuel close by. There's a coin very close by. The way that the authors have represented this as state space search is they've defined a state this way with 7 features. Each state is represented by the x position of Rob. So 5 is the state that we're currently looking at. The y position, 8, so this defines the position of Rob. This defines how much fuel Rob currently has. And this defines which coins have been picked up. So in this representation, it appears that coin C2 is picked up and none of the other coins have been picked up. If Rob comes down here, then Rob changes the y coordinate from 8 to 7. Rob has a little bit less fuel, but Rob has an additional coin. Okay, so one of the possible actions from this state would get Rob to create this state. And this is an example where this graph has not been pre-enumerated. The AI system is simulating the moves, and from this state is generating this state. So it's generating the graph that it's searching as it is searching for a solution. There's no notion of a pre-enumerated graph. There's another possible state that could be created, at least one other, there's several others. One would move Rob up here, changing the y location again, consuming a little bit of fuel. No coins have been retrieved here, but now Rob is in a better position through one of these children to, again, through a change of state, moving from here to here, getting fuel, but without picking up any new coins. Okay, so somebody has built an AI that will start with a given state like this, and the AI has been provided with a set of operators or actions that will allow it to change state. One possible action is to move up. One possible action is to move right. One possible action is to move down and left if there's no obstacle there. So there's some rules that have been built in that allow the AI to go from this state to potentially each of these states. And remember, the AI is searching a virtual space. The AI is not searching physical space. So all of these are candidates. What the AI wants to do is the AI wants to find a path from this to some ideal state in which all the coins have been picked up. Something that looks like this. All the coins have been picked up. We don't care how much fuel we have left, and we're at location 1, 1. All right. Been some rules that allow that, and it's searching virtual space. Once it finds a route from a given state to a goal state, it can then carry it out in real space or in the real context of a real game. So this you can think of as planning for the next step in a real game. Start state, some states that we've explored, some states that we've not explored, and then this notion of a frontier, which is the states that are candidate states that we're currently considering how to expand. So here's the generic search algorithm that we've been given. Again, frontier is a set of candidate states. Initially, frontier is just going to be the start node. While the frontier is not empty, while we still have things to explore, I'm going to select and remove a path from the frontier. So the way that this algorithm is written is this node in the frontier, we've highlighted it in red, but in actuality, what is stored at that node, or in this state that we're going to be selecting, is the path that got us from the start state to that node. So every time we take something off the frontier, we're actually taking off a path, a representation of the path from the start state to that current state. If we were to select this node next, we would be taking off literally the path it got from the start state to that node. Okay, so we're remembering the path that gets us to a node each time we pick off a path. So we take off this path, the next path, through some method. The method that we use is going to be what determines whether this is a depth first search, a breadth first search, a lowest cost search, or some other kind of search. If the very last node in this path is a goal, then we return that path. We found a way of getting from the start state to a goal node. We return the path, and the agent can follow that, can then follow that path from the start state, this place that it actually is. Remember, this is all planning. The agent is not acting in the real world when this process of search is going on. The agent is searching in a virtual world that mimics or is alike the physical world. And once it gets a plan or a sequence, a path from the start state to the goal node, then it can actually execute that path in real space. Okay? So if this final state in this path is a goal node, then we can return this path. Now, if we wanted to return a number of paths, not just one. If I plan a route from here to Charlotte, North Carolina, and I'm driving, I use Google, and it gives me a route. Google typically gives me multiple routes because Google doesn't know what my preferences are. One of the routes is going to be typically the shortest length route or the shortest projected time route, according to Google. But based on my previous searches, Google may know that very often I do not take freeways. I go back roads. And Google has learned enough to give me some possible back roads through Cherokee National Forest as one of my options. Takes a lot more time, but based on my preferences, it is going to provide that. It's going to provide some other routes too. And for all of you, if you were to use Google to plan a route, it would typically give you multiple routes. So let's suppose Google was using something like state space search. If it found a route, it would not simply necessarily stop there. What it might do is, instead of doing this return, it might add this path to a set of accumulated solutions. And when that set reaches a certain number of solutions, it then would return that set of solutions, candidate solutions, not one solution. So this literally need not be a return. It could be update the accumulated solutions and continue. But if NK is not a goal, we're certainly going to go and look at every neighbor of NK. We're going to add that to the path. Each of those neighbors we're going to add to the path, and then we're going to add that new path, each of those new paths, to the frontier. So if NK has 3 neighbors, and depending on the search, we might ask that have not been visited before. But in this particular algorithm, it doesn't matter whether they've been visited or not. We add n to the end of this path, and then we continue to search. We come back up here, this while loop, and we pull off another path. It may be one of the ones we just added, if this is a depth first search, or it may not be, if it's a breadth first search or something like that. How does this frontier ever become empty if we don't do a return? It may be that NK has no neighbors. It may be that NK is a sink. And if you reach a point in which all the terminal points and paths have no neighbors, or the only neighbors they've had have already been looked at, then you get a case where you're just going through paths and you're not you're not generating new paths in the frontier. At that point, after many of those, the frontier might become empty and you might exit unsuccessfully, having found no path. You notice something here that may seem strange, but it's nonetheless somewhat important. Notice when we check to see whether NK is a goal or not. We check to see whether NK is a goal when we take it off the frontier. We don't check to see whether N is a goal before putting it on the frontier. And that turns out to be important if we want to make certain guarantees about the optimality of what it is that we're returning. We'll probably talk about this more in the context of A*, which is what the reading you're going to do for Thursday. But nonetheless, this is a important choice in the algorithm design that just be aware of as you read. That we're checking to see whether NK is a goal when we remove it from the frontier, not when we put it on the frontier. Okay? The way that the book presents this is going to give the order in which nodes might be explored in a depth-first search and in a breadth-first search. So we take a look at a depth-first search. This is the root of this search tree is going to be the start node. And other nodes here will be goals. I would typically give these labels, and we'll talk about them, but these numbers represent the order in which the nodes would be visited in a depth-first search. And there's typically a right-to-left convention here, or left-to-right convention. That is, we're going to explore the left before we explore the right part of the tree. So what would happen here is this is the first node that we would explore. The frontier is initialized to be that node only. We would remove the path. There's going to be a single item in the frontier. It's going to be the path containing this node only. We're going to generate the neighbors of this node after removing it from the frontier. The neighbors are going to be this node and this node. So these two nodes, this is taken off the frontier, and paths to these two nodes are placed on the frontier. Suppose that this node is placed on the frontier first. Remember that in a depth-first search, the frontier is implemented as a stack. So we push that, a path corresponding to that node, and then we push a path corresponding to this node. So the second node that we're going to pop off the frontier is going to be this one. This will be at the top of the stack. When we pop that path off the top of the stack, we generate the neighbors of this node. They correspond to these two nodes. We push this one, and then we push that one. So the next one we're going to visit, the next node or path, 1, 2, 3, is going to correspond to this one. We pop that off. And so we can continue, and we're going to push these two nodes. We're going to pop that, push these two nodes, pop that. This has one descendant. This presumably has no descendants. And so we hit a dead end, and all of these, 5 has been already popped off. 5 is no longer on the stack. It was popped off before we generated 6. 4 is no longer on the stack. It was popped off when we generated 5. But what still is on the stack is this node, or more literally, a path to this node, which corresponds to whatever this node is, this node, this node, this node, that node. So this remains on the stack. We pop it off, we generate its children. So depth-first search is going to follow what is called a in-order traversal. You may have seen that in algorithms, or a pre-ordered traversal. It's going to visit this, and then it's going to visit the left subtree, and then it's going to visit the right subtree. T, U, Y, Q, W, R, V. Which of these will depth first search, as we've described it, find first? It will find T first. That's correct. Now, this left to right convention, moving from left to right in the way that you pop off nodes from the stack, that's simply convention. We could have obviously pushed on the nodes off in a different order, and we would have maybe pushed this first and then this. But we will use this left to right convention often. Nonetheless, here's an example of breadth first search. Again, it is following it's going to be putting on placing things on the frontier as it visits states, as it pops them off the frontier or takes them off the frontier. But the frontier in breadth first search is implemented as a queue. Oddly, we would place, in this case, this is one reason I am a little bit forgiving of conventions, because to make this work out in left to right order, you would put that on the queue first, and then you would put that on the queue. And so 2 would be removed in this case before 3. So in the stack example, in the depth first search example, we push that before pushing that. In the queue example, to make this left to right order work out, we place that on the queue followed by that on the queue. You understand what I'm saying? It's sort of the opposite convention to make it work in terms of this left to right removal from the frontier. I'm going to visit these level at a time. So which of these goals would breadth first search find? Who votes Q? If we're following the left to right convention. Yeah, it would find Q first. So in the reading, breadth first search is guaranteed to find a shortest length path to a goal. Depth first search is not guaranteed to find it. Depth first search can go running forever. On Thursday, you'll be reading about lowest cost search, and we'll talk a bit about that on Thursday. We can take a problem like this, and it seems quite natural to represent it as a graph, where each location corresponds to the node in the graph. And the adjacent positions imply arcs between those locations. So this mapping between location and a graph node is quite natural. Now, I sort of said the following. In this problem, notice that a state is not so naturally necessarily represented or viewed as a node in a graph. I mean, and in this case, this is a case where we're enumerating the graph as we go. This entire construct is a graph, or is a node. It's going to be a node in the search graph. Let's say that I had this situation, and I was trying to get from here to here. I might go from 05 to 07 to back to 05, 0105. Might go from here to here and then back again. And I illustrated that in the this graph here. I'm sorry, 03 to 01 back to 03. In this first problem, if you wanted to make sure that you were not visiting repeated states, you could just put a little mark at that location. So I'm at 0103, I go to 0101, but before leaving this, I put a little marker there, indicating that I've been at 0103. And so when I come back to it here, I can say, I visited this already. So in my planning, let's not consider this part of the possible solution. When I'm looking, because I've got that check mark there, let's only consider paths that don't involve repeating that state again, because that would be a wasteful move. And likewise, when I take 0101 and I generate its successors or its neighbors, I put a little mark there, indicating that I've been there before. In this other example of a problem, it's not, I can't simply leave a mark in what corresponds to a virtual location. I don't simply leave a mark at a node, because what a node is a node is a more complicated construct. It's not a very complicated construct, but this node in the search tree is a vector. But in general, the node in the search tree could be a complex graph itself. It could be a image. It could be some textual description. It could be a very complicated construct. This is just an example of a construct that we would have to check. And so if we want to check in repeated states like this, if we want to check for repeated states like this, what I would have to do is I would have to check for equality of vectors. So if I wanted to make sure that somewhere down here, if I encountered this vector somewhere down here, maybe after, or somewhere down here after getting gas and or fuel and then exhausting that fuel down in this subtree somewhere, and so I got a repeat of that node, an exact repeat. To check for repeated states in this search, I've got to check for vector equality. I've got to check if I want to avoid repeated states or guard against repeated states. Every time I generate a new state, I'm going to check to see whether that state has been something I've seen before. And if these states are even more complicated constructs, if they're themselves graphs or images, checking for equality and thus repetition in states can be very expensive. And so that can dominate the cost of the AI that's doing the searching. I don't have the luxury of just putting a check in a virtual physical location of an explicit graph. If I'm enumerating a graph as I search, there's really nothing to leave a check mark on. And so checking for repeated states becomes a more complicated process. One second.